Welcome back, class. So last time we looked at how to write and balance chemical equations, and now what I want to do is move into that idea of quantifying again, and we want to look at how we can use these now balanced equations to quantify the amounts of reactants and products that we might need or make in a particular reaction. Well, the first thing is to introduce what might be a strange word to some if you haven't heard it before, and that is this term stoichiometry. And basically all stoichiometry means is it is the study of the quantitative analysis of chemical reactions, right? So anytime we refer to these kinds of calculations we're going to do where we're going to quantitatively predict how much we can make or figure out how much of one reactant needs to react with another. This is called stoichiometry. So, one of the big things we learned last time was this idea that the coefficients in our balanced equations specify the relative amounts of moles or molecules of each substance involved in a reaction. So when this is moles, we call these mole-to-mole ratios. So these coefficients will provide us with these so-called mole-to-mole ratios. Now, of course, these ratios can also be applied to molecules as well, right? It's going to be the same ratios, just different units. So let's start by balancing this equation, and then we can do some calculations with it. So if we set out to balance it, we start with our carbon, let's say. So we got 3, and so maybe we need to put a 3 here to balance it. So we have 3, so let's look at the hydrogens. We have 8, so I have 2, so I can put a 4 there to balance it. So I got 4 in front of water. Now if I check my oxygens, I only have 2 here on the reactant side, but I have 3 times 2 or 6 from the CO2 and 4 times 1 or 4 from the water, so that's 10. So in order to get 10 on the reactant side, I need to put a 5 coefficient here. So now we have our balanced equation, and we have coefficients of 1, 5, 3, and 4. Now, by using these, we can develop ratios. So, for example, I could say that for every 5, and I'm just going to use moles, but this could be molecules as well. For every 5 O2, I can make 1 C3H8. Or I can write this in the other way. I could say for every 1 C3H8, I need to react it with 5 O2. And we can set up ratios between any of these. So, for example, we could also write that for every 3 moles of CO2 that I make, I need to react 1 C3H8. Or for every, to make 4 moles of water, I need to react 1 mole of C3H8. And of course, we could set up other ratios as well between oxygen and CO2 or oxygen and water. Right? The key is we can set up these ratios, and these ratios behave much like conversion factors. And they allow us to convert from one species to another, either whether that's in terms of molecules or moles, but it allows me to convert how much of one into how much of another. It is my conversion. Right? So, for example, this here is my conversion between how much C3H8 I have and how much oxygen. Right? It's going to be 5 times as much, always. Okay? So that's the idea. So let's continue on with this one. So it says balance the equation. Well, we did that. and we want to determine how much oxygen is needed and how much CO2 and water will be formed from this given amount of propane. So in every case, we're starting with our C3H8. Now, I'm not going to do all three of these for each of these examples. I'm just going to do a few to kind of get you used to the idea. So let's just look here and say, okay, I'm going to start with one molecule of C3H8. And let's say that I want to figure out how much oxygen is needed. So to do that, right, we're going to use dimensional analysis and our ratios. Right? So I need to convert between molecules of C3H8 and molecules of O2. To get my units to cancel out, right, I'm going to need molecules of C3H8 to cancel out on the bottom, and I want to end up with molecules of O2 that I need. Now, what numbers do I put here, right? And this is where we go back to our coefficients, right? And those ratios become directly from the coefficients, right? So I need 5, in this case, molecules of O2 to give me, to react with 1 molecule of C3H8. And now I can do the math, and that's simply 5 molecules of O2. So for every 1 molecule of C3H8, I require 5 molecules of O2. And I could go on and do this same calculation with CO2, or to form CO2, and how much water I would form using their particular ratios. But I'll use those ratios here, and let's do some other examples. Well, what if I start with some amount of molecules? Let's say 100. So let's say I have 100 molecules of C3H8. And this time, I want to focus on, the CO2. So how much CO2? So, again, I need my units to cancel, so I'm going to need molecules of C3H8 on the bottom. And since I want to get to CO2, I'm going to need molecules of CO2 on the top. Well, my balanced equation tells me that I can get 3 CO2, right, for every 1 C3H8. So we got 3 and 1. So that means if I react 100 molecules of C3H8, I can form 300 molecules of CO2. And again, I could do this with any of the ratios to go back and forth between any of the species. So what if I have 6.022 times 10 to the 23rd? So I have Avogadro's number of molecules of C3H8. And this time, let's focus on the water. So how much water can I make from 6.022 times 10 to the 23 molecules of propane? Again, I need my units to cancel. So I need molecules of C3H8 on the bottom, molecules, in this case, water on the top, because that's what I want to focus on. So if I go back to my balanced equation, my ratios, right, I'm going to make 4 waters for every 1 propane. So I have 4 water to 1 propane. Again, my molecules cancel, and I end up with 6.022 times 10 to the 23 times 4, which would be 2.41 times 10 to the 24 molecules of water. So we can see how these ratios are going to work, right? And so once I have the balanced equation, it unlocks the ability to do all of these conversions. And there's a couple things that will help us here, right? Is that we only focus on the two species that we're interested in. So in any of these problems, we're going to start with one material in our reaction, and we're going to try to convert it into some other material, either another reactant or a product. And those are the only things we need to focus on. So when I'm doing this problem to figure out how many molecules of water, then I don't need to worry about the CO2 and the oxygen, not for this problem. So let's say that I start with 1 mole of C3H8. Now, I started off calling these mole-to-mole ratios because this is most commonly what we'll be working with, right? You'll be using moles of these different reactants and products. So let's look at the oxygen, how much oxygen we need. So again, I need my units to cancel, so I'm going to need moles of C3H8 on the top, or on the bottom. I'm going to need moles of oxygen on the top. And again, I go back to and I have, the same ratio that I used up here, right? It's 5 oxygen to 1 C3H8. And if I do the math, my moles of C3H8 cancel out. I need 5 moles of O2 to react. Now, and I can do this with each of them. So this one I will show. So if I start with, again, 1 mole of C3H8, and let's say that I want to focus on moles of CO2 this time. So I need moles of C3H8 on the bottom to cancel. I consult my balanced equation and I see that I can make 3 moles of CO2 for every 1 mole. So I'm going to be able to make 3 moles of CO2 for every 1 mole of C3H8. And we'll just wrap this up by, what if I started with 1 mole of C3H8, but instead I wanted to figure out how many moles of water I could make. Now again, I still need moles of C3H8 on the bottom to cancel. So if I convert, I look at my ratio, I have 4 to 1. And so this is clearly, if I do my math, I cancel out my units. I'm going to end up with 4 moles of water. So starting with 1 mole of propane, I need to react it with 5 moles of water. I could produce 3 moles of CO2 and 4 moles of water. Okay? So the key here is understanding how these ratios work, right? And so the key is the balanced equation. Once we have the balanced equation, then we can we can take our ratios from those coefficients and apply them to various problems. So let's do some more examples. Okay, so we're going to stick with this same equation. So let's go ahead and write our coefficients in here. So we had a 1, we had a 5, we had a 3, and we had a 4. Okay, so we have our balanced equation. Now, the question says, if I react 50 grams of propane, how many grams of oxygen is needed? Well, so now we're doing a mass base, right? So in the previous one, we were going from molecules to molecules or moles to moles, and the key there is our ratio. But now we're going to combine these to some of the things that we learned in the last couple of chapters about converting moles into grams. So a lot of the problems that we encounter will follow this basic pattern, where we're going to start with the mass of some material here, and we're going to need to convert it into moles. And so, of course, to do that, right, we always need the molar mass of whatever the material we're working with is. Now, why do we need to get it into moles? Well, because we have to know the moles before we can apply the mole to mole ratio here from our balanced equation. And that's going to allow us to go from moles of A to whatever we're trying to target. And then most of the time we're going to express this as in a mass, and we're going to need the molar mass of B to do that. Now, and the reason we focus so much on this is because in real life, right, in labs, this is what quantities we have to work with, right? We're going to weigh out grams of something. We're going to isolate grams of some product, right? We can't use moles in sense of actually quantifying things in real life, right? We need moles to do the calculations, but we can't put it on a scale and weigh moles, right? We weigh grams, and then we have to put that in terms of moles in order to do the calculations or to work with our reactions, because our balanced equations are in terms of moles. So now that we have this basic pattern, let's apply it to our problem. So we're going to do this one here. So we're going to start with 50 grams of C3H8. Okay. And we want to figure out oxygen, right? So the only things we care about right now is the propane and the oxygen, right? We're not concerned with how much carbon dioxide, how much water, right? That's a separate problem, right? So, but in this particular question, we want to convert from how much propane we have to how much oxygen we need to react with it. So, the first step is to put this propane in terms of moles. And of course, in order to do that, we need grams of C3H8 per mole of C3H8. Now, in order to do that, we need the molar mass. So what's the molar mass of propane? Well, let's calculate it here. So we have 3 times 12.01 grams for the carbon, plus 8 times 1.01 grams for the hydrogen, and that calculates to 44.11 grams per mole of the C3H8. So 1 mole is equivalent to 44.11 grams. Now, when I do this calculation, right, that's going to cancel out my grams. Now, I could stop here and get an answer, and you'd come up with, something along the lines of 1.133 moles of C3H8. But instead of doing that, we're just going to continue on with the calculation and do the next step. So now that I have moles of C3H8, now I can do my next step, moles of A to moles of B, and my B here, right, is moles of O2, moles of C3H8. So I need my ratio. So I go back to my balanced equation, and I see that I need 5 moles of O2 to every 1 mole of C3H8. So at this point, my moles of C3H have calculated out. And again, we could get an answer at this point, and we would get approximately 5.67 moles of O2. But we're just going to do this as a string of calculations. Now the last thing, right, is now I have my moles of O2, but it asks for grams of oxygen, right? So So I have to convert this into oxygen. So I need moles of O2 down here, grams of O2, that's my desired. So I need my molar mass of O2, and that's going to be 2 times 16, 32 grams per 1 mole. My moles of O2 cancel, and I'm left with 32 with grams of O2. So if I follow through my math, I take my 50 divided by 44.11 times by 5 divided by 1, and then times by the 32, we end up with 181.36 grams of O2. Now, significant figures, I'm going to have 3 from my original value. So that means I have 181 grams of O2 is how much I need. Okay, so that was the first question. So the second part says how many grams of CO2 in water will be formed? So let's lay these out. So these are going to follow a very similar pattern, right? So let's realize here that, the first step is going to be the same, right? Because in every one of these, I'm converting to moles of C3H8. And so this first step is going to be the same in all of these calculations because I have to get from the mass of propane into moles of propane. Now where we start to differ is because of what my target is. So let's do CO2. So my target here is CO2. So I need my mole to mole ratio between moles of CO2 and moles of C3H8. Now for my balanced equation, it's 3 moles of CO2 for every 1 mole of C3H8. And so my last step here is to put this in terms of grams. So I'm going to need my molar mass, my grams of CO2, my moles of C3H8. Now, we've done this previously, but the molar mass of CO2 is going to be 44.01 grams per mole, right? 1 carbon, 2 oxygens. So we cancel this out. I do my calculations. I should end up with 149.65 grams of CO2, or to significant figures, 33, 149, the 6, I get 150 grams of CO2. Now this is a little tricky, right? I can either put a decimal place there, or maybe better would be to write this in scientific notation as 1.50 times 10 to the second grams of CO2. Now, lastly, we'll show the example for water so that you can see all the math. So, this is going to look very similar. So, 50 grams of C3H8. I'm going to convert that into moles. 1 mole C3H8, 44.11 grams of C3H8. Now, since my target here is going to be water, I'm going to have my moles of water, my ratio of moles of water to moles of C3H8. And from my balanced equation, that's 4 to 1. And then lastly, I'm going to use my molar mass of water to convert into grams of water from moles of water. And that molar mass, right, for water, 18.02 grams for every 1 mole. Right, if I check my dimensional analysis, my grams of propane cancel out here, my moles of propane cancel out here, My moles of water cancel out here, and I'm left with grams of water, which is what I want. So if I do this, I end up with 81.61 grams of water with significant figures. Gives me 81.6 grams of water. Right? So we can see these calculations, right? And while I showed these and they seem kind of repetitive, the more you can see this, the more you can practice it, the easier it becomes. But what I want to point out is the pattern, right? The pattern of these types of problems is very similar, right? We're starting with a mass of one thing. We have to convert that into moles so that we can use our balanced equation to translate that, if you will, into moles of something else using the coefficients, using our mole-to-mole ratios. And then we can, if desired, express that moles in terms of grams, right? So sometimes the problems may ask you to stop with moles of whatever we're trying to figure out, moles of oxygen or CO2. Other times it may ask you to do grams. But we have this pattern. And so we saw the first step was always the same, right? What really differs is when we start translating it into something else, we have to use the appropriate ratio, right? Depending on what we're trying to figure out. And we have to use the appropriate molar mass to convert it into grams. Okay, well, let's do just a couple more practice problems because, again, this is going to be something that we're going to do a lot in this course, and so I want to make sure that we get plenty of examples. So let's try these couple problems. So our first one, we have solid sodium metal reacts with diatomic chlorine gas to form solid sodium chloride. If we have 9.2 grams of sodium, how many grams of sodium chloride can I make? Okay, so the key here, one of the keys, right, is we're going to be starting with grams of sodium and we're going to translate that into grams of sodium chloride. Well, of course, the first thing I need is the balanced equation. So we had sodium metal, and that reacted with, now I specified diatomic chlorine gas, right? At some point we need to realize that chlorine is one of our diatomics, right? So it's always going to be Cl2. And we form sodium chloride, right? And so the ionic compound between sodium chloride, since sodium is always a positive 1 and chlorine is always a negative 1, right, is NaCl solid. Now we need a balance, so I got one sodium, but I got 2 chlorines and 1 chlorine. So I need to put a 2 here, right, to balance my chlorines. Well, that changes the sodium to 2, so I'm going to have to put a 2 over here to balance out the sodium. So I have my balanced equation, and now I can start to do my problem. So I said that we're interested here, right, in the relationship between sodium and sodium chloride. So the ratio that we're going to be interested in here is that ratio between sodium and sodium chloride. So let's go ahead and do the math. So I'm going to start with my 9.20 grams of sodium, and I'm going to convert that into moles. Well, 1 mole of sodium, right, if I look on the periodic table, is 22.99 grams of sodium. So that's going to cancel out my grams of sodium. Now, to translate that into moles of sodium chloride, right, I need my ratio. So my balanced equation tells me that for every 2 moles of sodium, I can make 2 moles of sodium chloride. So now we're at moles of sodium chloride. We want to convert this into grams. So we're going to use the molar mass. So we have grams of sodium chloride here per mole of sodium chloride. And if we do the math, we add up sodium and chlorine. So that's 22.99 grams for sodium plus 35.45 grams for chlorine. It's going to be 58.44 grams per mole. So I got 58.44 grams per every 1 mole. Yeah, my moles of sodium cancel. So my dimensional analysis shows that yes, indeed, I should end up with grams of sodium chloride. And if we do that math, we simply plug in our 9.2 divided by 22.99 times 2 over 2, right? So that's really a ratio of 1, so I get times 2 divided by 2 times my molar mass of sodium chloride, 58.44. I can make 23.39 grams, but significant figures. 3 of them, I can make 23.4 grams of sodium chloride. Okay, so one last problem here. So I have this reaction of methanol. It burns in the presence of oxygen, so methanol reacting with oxygen to form water and carbon dioxide. So another one of these combustion reactions. So let's write it out. So I have CH3OH, and that's a liquid, it's a fuel, liquid, right? Plus O2 gas goes to carbon dioxide gas plus water gas. So let's balance. So carbon, 1 and 1. Hydrogen, now we've got to be careful here. I have 4 hydrogens here. 3 here, 1 here. Right? So I have 3 and 1. So I have 4. So that gives me, I can put a 2 here. Right? To balance that. Now let's check out the oxygens. Well, on the reactant side, I have 2 from my O2, but I can't forget about the 1 here in my methanol, so I really have 3 over here. And the product side, I have 2 from my 1 CO2, 2 from my 2 water, so I have 4. So I have 4 and I have 3. Well, there's no number I can put in front of O2 to get this, right? There's no way I can put the 4. So if I were to change this to 2, it would mean I'd have 5 over here. And so I could put 1.5 here, right? So I could put 1.5 here, but that's not really going to help me. Now, this is something we encounter a lot with combustion reactions. So one trick here is that we can often make this work out by simply doubling what we're reacting with the oxygen. So I can put a 2 here, and now that gives me 2 carbons. So I can change this to a 2. It gives me now 8 carbons, 8 hydrogens. Right? So this can change to a 4. Now on this side I have 2 times 2, 4 oxygens from my CO2, 4 times 1 of 4 from my water, so I have a total of 8. Now remember, I already have 2 in the methanol, So that means I need 6 more, or I can put a 3 here so that I end up with 8 oxygens on both sides. So now I have my balanced equation with coefficients of 2, 3, 2, and 4. And now I can set about solving the problems. Now, I wrote this one just a little different, just so you can see that, as long as you follow the units, things will work out. So in this point, in this one, instead of giving you a traditional mass, I said that 1 gallon of methanol equals 94.5 moles of methanol. And I want to know how many moles of oxygen would be required to react with 3 gallons of methanol. So a couple keys here, right? The 2 species that we're interested in is the methanol and the oxygen, right? So that's where my ratio is going to have to come from. Now, as always, I need to get moles of methanol because that's what I know. So I'm going to start with what I know, which is 3 gallons of CH3OH. Now, traditionally here, we would use a molar mass to convert to moles. But I don't have grams, right? I have gallons. So we're given the conversion to do this, right? Because I can go from gallons of CH3OH into moles of CH3OH, because I was told that every 1 gallon is 94.5 moles of C3OH8. And my gallons cancel. So while the units might be a little less traditional, right, the key is I've gotten into moles, right? And so now I can go from moles of C3H8, I can switch into moles of oxygen, right? That's my next step. So now I'm going to go to the equation and use my ratio. So I'm going to want moles of oxygen on the top, moles of methanol on the bottom, and my equation tells me that there are 3 O2s for every 2 methanol. And this particular problem, that's what it wanted. It wanted moles of oxygen, so I can stop here, right? Because my dimensional analysis tells me that I should end up with moles of oxygen at this point. So I'm going to do my math. 3 gallons times 94.5 over 1, and then times 3 divided by 2, and we should end up with 425.25 moles of O2, or with significant figures, 425 moles of O2. And that would be the answer to the problem. Now, we could clearly convert this into grams of O2 if that's what the problem had asked us to do using the molar mass, but it didn't in this particular case. So a little different version of the problem, but with the same basic ideas of those mole to mole ratios, right? Those coefficients of our balancing equation being the key. All right. So now you've seen a few examples. Again, practice. And in the next section, we're going to talk about, again, more of these kinds of problems, but with a little different twist.